Hello and welcome to part 4. So in part 4, we are going to be focusing on this whole slew of reactions that are all going to revolve around making something called a diazonium salt. So this is something that in lab, when we do the azo labs, this is the reaction that we are doing. This diazonium salt has a lot of interesting synthetic purposes. We can replace that little diazonium piece with a number of different functional groups, and we can also couple it to other benzene rings, and that's how, like, for instance, that's how we make our azo dyes. So to dive into how to make this diazonium salt, let's look at the reagents that are needed. So we are looking at a reaction of a primary amine, so I'm going to use aniline here, and reacting it with something called sodium nitrite and hydrochloric acid. And this is going to yield this diazonium salt. Sorry, that does not have a minus charge. What is wrong with me? This nitrogen has a plus charge. Do please fix that. There we go. The diazonium salt. You wind up having like a chloride anion as your counter anion. Okay. Now, to make this, it's actually a relatively, it's not a short mechanism. It's a little bit of a longer mechanism. And so the story really begins right here with the starting materials. The sodium nitrite and the HCl are not what is directly reacting with the amine. So let's look at what they're actually doing. You're making something called a nitrosonium ion for the nitrosonium ion. Okay. Again, we're not even touching the amine yet. You are taking your sodium nitrite, which is NO2, so you wind up with this O minus right here. Now, essentially, you're just making that oxygen into a better leaving group so you can kick it off. So even though this mechanism altogether is quite long, it's mostly proton transfers and trying to kick off oxygen. So we're going to use our HCl, and we are going to grab that proton. I am going to not change the color. Let's not worry about that. Okay. Oh, there it is. All right. Sorry. I knew it's been a minute since I've recorded. So we're going to pick up that hydrogen, and that is going to give us this protonated nitrite intermediate, or nitrous acid, I suppose. And then it's going to just happen again. So we're going to take HCl, because OH is not a great leaving group, at least not an acid. And so we're just going to pick up yet another proton. Now that is going to leave us with this protonated nitrous acid. You see water now. That we know is a great leaving group. And it does. It just kind of falls off, right? And we lose water. Right, so minus water. And then what you're left with is called a nitrosonium ion. Now this is split up on the slides. I'm going to keep going on my blank slide of this side of the screen, but you can see that this nitrosonium ion is not very stable. That's why we can't just buy a bottle of nitrosonium ion. We have to make it from nitrite and HCl. But this is going to be just perfect to react with the amine. All right, so there's the little resonance structure. Thank you. for the nitrosonium ion. Okay, so it's extremely electrophilic, very unstable. Again, why we can't buy it in a bottle, why we have to make it. But it will react with the amine immediately. It's a very fast reaction. When you guys did this in lab, you put the nitrite and the HCl in one test tube, and you put it on ice because it is very, very reactive. You want to slow it down just a little bit, and then you could put your amine. You used either metanylic or sulfonilic acid. But then that amine, and I'm just going to use aniline because that is what we are going to be focusing on later in the chapter. Your aniline will come in, it's a good base, good nucleophile, if you remember back from Organic 1. We've also used it as a good nucleophile in Organic 2. It is going to come on in and attack your nitrosonium ion. Now it will attack the nitrogen and then let's see what that makes. We're headed towards something called a nitrosamine. You can see right here. This is going to form that new nitrogen-nitrogen bond. So this still has its hydrogens here. And now it is connected to this NO. So this is a plus charge. We are going to get a neutral intermediate. So there is water around, right? If anything, we lost water in the last step, plus HCl is an aqueous solution. The sodium nitrite is usually an aqueous solution as well. Water is going to come along and snag that little proton for us. All right, give those electrons back. And now we are left with, I'm going to have to do this one on 2 slides. She's a big mechanism. All right, so this is our nitrosamine. So it's neutral, it's got that N-N bond, but it still has a double bond to oxygen. All right, so the N-nitrosamine. Right, N lets you know that nitroso group added to your amine. That's where they're bonded. Now, this nitrosamine is also not very stable. You get like a little break in the mechanism in the slides here to let you know they are potent carcinogens. You have this nitrosamine in tobacco smoke. We know that smoking cigarettes has correlations and ties to different cancers, especially lung cancer. But you also find nitrosamines in small amounts in other places that you might be surprised to learn, like in your different food products and even in fried bacon. It's all an issue of like quantity and amounts, of course. But potent carcinogens in part because they're very reactive. And so they do fall apart. So why are we showing the amine plus the nitrite and the HCl forming the diazonium salt? We obviously have not finished that mechanism because over here we're just to the nitrosamine. So how do we lose that oxygen? Well, kind of like we lost the first oxygen from the nitrite. We're going to protonate the heck out of it and lose it as water. And so we're going to follow this along. I am going to just start with my N-nitrosamine right here. N-O. There's still an H. Okay, so again, where this is picking up is right here. Right? They just overlapped the mechanism a little bit. So we're still in acid, right? So you can do H3O plus, HCl, just H plus. We did make hydronium in the last step, so I'll go ahead and use that. The nitrosamine picks up a proton. And we're on our way to getting it closer to being a good leaving group. We're not all the way there yet. Because again, we're in acid. So a hydroxide is not going to be the easiest thing to lose. So then before we give it another proton, because it's already got a plus charge, it's got 3 bonds and a lone pair, what we're going to do first is we're going to do a little solvent-mediated proton transfer. So this proton attached to the nitrogen, it's going to get moved, but we're going to show it moving through the solvent, right, rather than just picking it straight up or switching it intermolecularly. So grab it with the water, give those electrons back to the nitrogen. So you wind up with a negatively charged nitrogen here. What am I doing? Oh no, I missed a step. Hold on. I didn't want to keep drawing arrows and show that I was wrong. Here we go. We are picking up that hydrogen. We're just not going to make a charge on it, on the nitrogen. Here we go. So sorry. Please bear with me. There we go. Put everything back. Now, I messed up my arrows. Let me show you. So instead of just giving that lone pair to the nitrogen and having a negative nitrogen, we're kind of doing a little bit of a resonance shift here too. Those electrons could be shared between the 2 nitrogens, which would then give that lone pair to the oxygen. So instead of creating an intermediate with a negative charge and a plus charge, we're just showing the flow of electrons to the more stable, neutral resonance structure. So we wind up with nitrogen with a double bond instead of 2 lone pairs and a charge. So we're creating these multiple bonds between the nitrogen. We ultimately want a nitrogen-nitrogen triple bond, so we are just on our way there, right? We're slowly making this oxygen into a good leaving group and creating our triple bond. So now that we have this intermediate, we're just going to protonate it again. All right, so we used hydronium, we made it again, we're going to use it again, so I'm just going to put my H3O plus down in there so that I can show this little proton transfer. All right, we're going to now get to that water leaving group. All right, we have nitrogen with a lone pair, double bond attached to this awesome leaving group that is water. And so all that needs to happen now is it just basically falls apart. We create the triple bond and lose the water. Minus water. And now we are to our diazonium salt. Right, again, there's a chloride ion floating around to balance that charge. It is a long mechanism, right? It is these 2 slides. You're going to make the nitrosonium ion, react it with the amine to make the nitrosamine. The nitrosamine goes through a series of proton transfers to end with the diazonium salt. This is the mechanism that you need, right? I won't ask you in a test to go beyond that. This is certainly enough, right? So I may ask you to show me how to make the diazonium salt. Okay, why did we do all that? Why did we do this long mechanism to show this diazonium salt? Well, because the diazonium salt can be replaced with a lot of different things. And there are 7 different functional groups that we can replace that N2 with. 4 are going to come from something called the sandmeyer reactions. You can make what is the word I'm looking for? A bromobenzene, a chlorobenzene, iodobenzene, and cyanobenzene using copper salts with diazonium salts. So we know a way to put on bromine and chlorine already. This is just another option. But we also now have a way to put on iodine and a nitrile, which we have not had a way to put on iodine before. So this is new. And a nitrile, we could have cheated around making a carboxylic acid and going through some chapter 20, right? Carboxylic acid derivative reactions. But this is another option, and perhaps even a more straightforward one. For instance, look how you could use this. So we know how to make an aniline, right? First, we have to put on a nitro group, H2SO4. That's a chapter 17 reaction, right? That's going to make a nitro group. And then we can reduce that to an amino group, to aniline, with a number of different reagents. A lot of times you're going to see FeHCl or zinc and HCl. You might use zinc mercury amalgam in HCl if you're also doing a Clemmensen reduction. Because the amines are basic, you are often going to see this with a second workup step of sodium hydroxide, just to make sure that you have that neutral amine. And then once you have that amine, right, you can do NaNO2 and HCl. You're going to use this one a bunch. And now you have your diazonium salt. And now you can just react it with any of your sandmeyer reactions. So like CuCN, for instance. Now we have a relatively, I won't say short, a reasonable synthetic route to making a cyanobenzene. And you can see how this could be useful here. Here's another example. There's no way to put both of these carbon groups on and then get a carboxylic acid. Now we know how to make a carboxylic acid on a benzene ring directly. You can put on a methyl and then you can do an oxidation, right? Sodium dichromate, as long as that carbon right there had a hydrogen on it. The problem is it would also transform that isopropyl group. And if you put the carboxylic acid on first and then tried to add the isopropyl, you would get a meta direction. So we have to be creative here. So first, we start off the isopropyl group already on. Then we can add so we're doing nitro, amine, diazonium salt, right? So we can get that diazonium salt. We can do the sandmeyer reaction. So we can put on that nitrile, and then you can hydrolyze it. So it gives you some more flexibility in making different substituted benzenes, right? As organic chemists, this is always exciting to have more control over where our functional groups are going to wind up. The sandmeyer reactions, right, that's 4. I mentioned there were going to be 7. There are 3 more. So when you are taking your diazonium salt, let's just summarize them here. So this could also be written N2+, but I'm going to draw it out. So we can use copper bromide. We can use copper chloride. We can use copper iodide. We can use copper cyanide. We can also use HBF4. So you can add fluorine now. This is exciting. Not with copper fluoride, but HBF4. So it's a little bit different. It's not a sandmeyer reaction, but it's a similar situation where we are just replacing that N2 with something else. You can also treat it with water and get a phenol. You can also treat it with something called phosphorus acid, I believe, H3PO2. And you can just knock it off completely and leave a hydrogen. All right, so 7 different ways to replace this. We can get bromine, chlorine, Iodine. I really picked a long way to do this, but I wanted to have it all on one slide. The cyanide. Right, now we finally have access to a fluoride. We can make phenols this way. We've only been able to make those with NAS reactions, and there had to be nitro groups in certain positions there. We could also use it strategically to guide other things onto the ring and then just knock it off with H3PO2. So we have lots of options here by just making this one intermediate. So yes, it's a long intermediate to make that diazonium salt, but man, it opens up this whole, other door of different modifications you can do to that benzene ring. One last thing that I want to show you is called the azo coupling. Right, this is what we did in lab with the azo dyes. As it turns out, that diazonium salt right here is also a really good electrophile. So in chapter 17, we did all of these different EAS reactions, nitration, bromination, Friedel-Crafts, etc. And we had to make a really good electrophile to get benzene to react. Well, this is a really good electrophile, and benzene will react. So all that's happening here is, actually, let's not put that underneath. I'm not going to do the mechanism. You are taking some sort of benzene ring and coupling. Now, in the example on the slide, it's phenol. And so the OH, you have to recognize that's an OP director. The this guy is really big, and so you're more likely to get para. I would also take ortho. It's just important that you recognize this is an OP director. So you wind up getting this coupling where it adds to that para position, and you wind up with a double bond in your nitrogens. Here we go, and that other ring. It goes through, we've already seen this mechanism. I'm not going to ask you for it on exam 4 of the final, but you have done this mechanism before, right? This EAS reaction. You have the electrophilic attack. You have the sigma complex, right? This resonance stabilized sigma complex. Then the little chloride ion, which was just your counter ion, is going to act as your base, right? And you're going to regain aromaticity and then have a little bit of HCl byproduct, right? You can do this with any number of benzene rings. And it makes some really cool dyes. You guys saw in lab, we had yellows and oranges and reds. All of that conjugation through both rings and then through that azo coupling here in the middle leads to a lot of kind of bright, brilliant colors. Varying the substituents, so we had like a sulfonyl group. You may have used naphthol, which has another benzene ring, or salicylic acid, which has some different functional groups. All of the ways you could modify this structure can change the color, can affect the color. And I'm going to throw this here at the end of this video because it would make too short of a second video. And that is the nitrogen heterocycles. Nitrogen heterocycles is a whole branch of chemistry we could go into. They with like a really vast, colorful amount of nomenclature. I want you to know 4 of the kind of most common heterocycles, and I just want you to know their names. So here we're seeing Nexium and Viagra as just, here are some examples where you're going to find heterocycles. And if I haven't defined it before, heterocycle just means a ring that has something other than carbon in it. So when I was in grad school, I took a class on heterocycles. We looked at oxygen-containing rings, sulfur, phosphorus, nitrogen. And when you add heteroatoms to the ring, the parent name is going to change. And so there are a lot of parent names. Again, I'm going to ask you to know 4. We aren't going to do the reactions of them, but I do want you to know pyrrole. We have discussed pyrrole before. It's an aromatic amine, right? It's also makes it not a very good base because that lone pair is involved in the aromaticity. We have another 5-membered ring. It's also aromatic, but it has 2 nitrogens in it. It's called imidazole. So 2 nitrogens. It has, let's see. Oh, I did that wrong. It has 2 double bonds. So 1 nitrogen has a lone pair and it's in a double bond. 1 has all single bonds and a lone pair. Imidazole. Imidazole is another very common and important heterocycle. You see it here. It's part of histamine, which might be a compound that you're familiar with, especially if you deal with allergies. We also looked at pyridine. Now, we've used pyridine quite a bit. It's a decent base. That lone pair is not involved. I'm going to write the name up here. Pyridine. There we go. And so this gets used as a proton sponge in a lot of reactions we've covered throughout the year. It's also a very common heterocycle in larger biomolecules, as well as our 4th and last structure, and that's pyrimidine. Pyrimidine is another 6-membered ring, but it has 2 nitrogens in it, right? Pyrimidine is an important base in biomolecules as well. You see them in DNA base pairs. So if you go on to biochem, you might be working quite a bit with pyrimidines. These 4 you can add to like your nomenclature section. I may give you the structure and ask you to name it, or give you the name and ask you to draw it. So please know those 4 as we work our way towards exam 4. We already covered all the spectroscopy that we are going to cover, but don't forget there at the end of chapter 22, you do have some good review slides, right? So review of all your amines, and then also getting into the Sandmeyer reactions and what you can do with diazonium salts all the way up to the coupling. And that is going to be it for chapter 22. Thank you.